There we go.
Got it?
Yep.
Damn,
Okay, so reflection and refraction.
Oh, God.
Today we're talking about reflection only. We'll get to refraction on Monday. So we'll start with reflection. A reflection is when a wave reaches the boundary between any two mediums. It bounces back into the first medium, at least part of it. We saw this when we tied the string to the slinky in that experiment, but I'll get to that in a second. But if I tie a rope to a wall and I send a wave down it, when it hits the wall, it's going to send a wave back. Because it's hitting the boundary between two mediums, that causes a reflection. And now, the reflection is based on the rigidity of the mediums. That means how hard it is to move them, how stiff they are. If the second medium is very rigid, like a wall, then almost all the energy, or all the energy is going to be reflected instead of moving into the wall. You hit the wall, the wave reflects, it doesn't go through the wall. If the second medium is less rigid, like say a small spring tied to a heavier spring, or a string tied to a slinky, then only some of the energy is going to be reflected. And some will continue to transmit through. So you can see that here. You get this big wave. It hits the larger string. Part of the wave energy is reflected, and part of the wave energy goes through. Okay? If it's a big wave starting on this side, when it reaches the string, part of it comes back, and part of it goes through. It gets bigger because this one's more rigid.
Is that what we're going to be doing today?
No. We're using yours.
Oh.
So this is what a reflection is, when the wave bounces back into the first medium after hitting a boundary between two mediums. Now, reflection would be very easy to understand if the world was in two dimensions. This is two dimensions. But the world is not in two dimensions. It's in three dimensions, so reflection gets more complicated. But before I get to the third dimension, let's just add on to this.
What would we look like if we were in two?
Now all waves,
Stanley.
guys, all waves reflect. Light waves, ocean waves, sound waves, water waves, all types of waves reflect. But we're going to be concentrating on lights because that's the one we understand best for reflections.
Is that bottom picture?
So, I'll explain in a second. For lights, metal surfaces are very rigid to light. So very rigid to light. They're not rigid in a normal sense, they're rigid to light. So almost everything gets reflected off it. That's why when you see a mirrored surface, this metal object, the image you can see is very clear. Because almost everything comes back, because the metal is very rigid to light. For other substances like glass and water, they're much less rigid to light. So most of it or some of it goes through, and only part of it is reflected. So you can see this person's behind a window, but you can still see part of the reflection of the stuff on this side reflecting on the window he's standing behind. Because a little bit gets reflected back, but most of it goes through.
Looks like a transition of a scene in a movie.
Yeah,
That's what it looks like.
probably from a movie. I'm just saying, I just wanted to illustrate, you've all seen this in water, you can get a reflection, but it's nowhere near as good a reflection as you get in a mirror or a metal object. Because not all of it's going through, most of it's going into the medium, but a little bit's being reflected. The book actually says for glass, it's like, at a 90-degree angle, it's like 2% gets reflected, and for water, it's like 4% gets reflected.
So water is more rigid.
A little bit
No,
more
it's
rigid to
not
light. Yep.
rigid.
What's the percent?
Remember, the rigidity to light depends on how the electrons are oriented in the object. In a metal, the electrons are free, so they're very rigid. When the electrons are stuck well to the elements, they're much less rigid to light. So let's get to three dimensions here. For three dimensions, we have what's called the law of reflection. It is a common sense law, but a lot of people get confused by this. First things first, let's think of light as a straight line, a ray. light moves in straight lines. It doesn't turn naturally. We think of a straight line as a ray, so it's a line that's going in one direction. And for reflection, we break it into two parts. The incident ray, which is the light before it hits the boundary, and the reflected ray, which is after it hits the boundary. On this picture, incident is turquoise, and reflected is purple. This orange thing is our object. I'll talk about the normal in a second. They call it the interface or reflecting surface. It could be anything.
And normal is the perpendicular to the
Yes,
interface.
we'll get there. Okay, so what the law of reflection states is that the incident ray and the reflected ray create equal angles on both sides of what's called the normal. The normal is a line perpendicular to the surface it's hitting. So this angle right here, they call it delta or theta I, is equal to theta r, which is
Theta I, theta
is that theta? Okay, theta I and theta r. They're equal. These angles to the normal are equal. So if I made this one steeper, what would this one do?
Get steeper.
Would it go to the right or the left?
Left.
So if this one's further down this way, this one's further down this way.
You said steeper.
That's like a
No, you
mirror.
said
Yeah.
steeper.
Oh yeah, if I move it closer.
Yeah, that's, yeah.
If it comes directly with the angle, where does it reflect back?
Directly with the
Yeah, because 0 degrees, 0 degrees. It's equal to 0 degrees.
Like a mirror.
Yep. Oh, yeah, it's a mirror.
Mirrors are cool.
This is how mirrors work. Anyways, we call this the angle of incidence, and this is called the angle of reflection. And this works for all surfaces. Even if the object they're hitting is round. You just break up the ray, or the light, into individual rays, and treat each individual portion as a flat portion. The law of reflection. So, mirrors. For a plane, otherwise known as a flat mirror, like this, you trace the lines to figure out where the image is going to be. The image is what you see in a mirror. We call it an image because it's not a real object. It's just a picture of an object. For a plane mirror, we call it a virtual image. Because to our eyes, it appears that that image is behind the mirror. It's coming from a place that no light is actually getting to, or at least not the light we're seeing is. And this happens because our eyes read light as being moving in straight lines at all times. Our eyes can't see the reflections, the turning. So what happens is your eye traces the line back to where it should be if it was a straight line.
It's really standing real straight.
Straight line. Even though the light is actually reflecting, our eye sees it as going back. So the image appears to be the same size as the normal object in the plane mirror, and the same distance behind the mirror as the object is in front of the mirror. So, if I'm standing 4 feet in front of the mirror in my bathroom, how far away does my image look like it is? Tyler? If I'm standing 4 feet from my mirror, how far away is my image appear to be from me? How far? 8 feet. Right? 4 feet to the mirror and then 4 feet behind. So it'd be exactly the same as standing next to a person who's 8 feet from me. It'd be the same concept.
So you just double it.
Yeah, because it's the same distance to the mirror to the image, or where the image appears to be. It's because you trace these lines in a straight line. Now, there are also types of mirrors called convex and concave.
A spoon.
Like a spoon is both. A convex mirror bows out, curves outward. A concave curves inward. We're not going to get into lots of detail about them, but convex mirrors and concave mirrors can shrink the image, make the image smaller or larger. They can flip the image over. They can make the image appear to be further behind or closer.
How can they flip it? 'Cause I just wanted to know how do you...
It's because you follow these diagonals, these lines. We'll do an experiment probably next week, or a worksheet or something about it. and you can see where the lines look like the image flipped over. Is how it, if you trace the lines back in straight lines. Okay? Anyways, we're not going to get into lots of detail about concave and convex mirrors, but for a plane mirror, the important thing is it's called a virtual image because it's coming from a place where there's no actual light, and it looks like it's same distance and same size. Diffuse reflection. Most objects do what's called diffuse reflection and not normal reflection. And that is because when light or any other sound wave hits a rough surface, or at least rough to them, each light ray is reflected away differently. So you can see it here. If it's not a flat plane, this ray hits and bounces that way. That ray hits and bounces that way. That ray hits and bounces different way. They all bounce in different ways based on the law of reflection. Because remember, each little piece counts as flat. When they're all different little rough, they're all going to be bounced in different directions. We call this diffuse reflection.
Like
When it's-
broken glass, like on the ground?
Well, this is like grass or dirt. That's why you can't see an image in it, because the light is hitting it, but it's all the rays are going in different directions. So you don't get an image. So we call this diffuse reflection. That's why you can still see most objects, even though you can't see a reflection in them, because the light's bouncing in all directions because it's rough.
Interesting.
And some surfaces can be rough to some types of waves and not others. It's usually based on the type of wave or their wavelength. For example, this radar dish. Does it look reflective?
No.
Like, would you say that this is a reflective surface?
Yes.
No.
No, most people would say, no, you can't see yourself in that.
But it reflects sound.
But it reflects radio waves.
Or radio.
Because radio waves have very big wavelengths, and they reflect. Radio waves see this as a mirror. But light waves don't. Light waves are too small, and they pass through it or see as rough, diffuse. So you can be reflective or polished to only to certain types of waves and not others. One last slide, guys. Okay. So sound can be reflected because sound is a wave. We call the reflection of a sound an echo.
Whoa.
Echo is a reflected sound. Sound reflects from all surfaces. Anytime a sound wave hits something hard, any other surface, it's going to reflect a bit because it's changing mediums. And it's different how it reflects off each material and shape of materials.
Isn't there like a point in every single room where you can whisper and no one can hear?
Usually. We call the study of how sound waves bounce around a room acoustics. So if you ever heard people talk about acoustics, they mean how the sound waves are bouncing around the room, or reflecting off surfaces. When you get waves reflecting multiple times and interfering with each other, what happens is the sound gets all garbled. You can't understand it, it's incoherent, and we call that reverberations. Reverberations is when the sound gets all interfered badly. That's a destructive interference. When you have constructive interference, which is what they build concert halls for, you bounce the waves off important points so everyone can hear just as well.
That's why they have like little.
So these concert halls are built very specifically to satisfy a variety of acoustics. Okay?
You should be in choir, Jake.
You're amazing.